Today we're going to talk about inverse functions and specifically the definition and how to deal with inverse functions in terms of a graph. So inverse functions. Two functions are inverses if when you substitute one function into the other, you get back x. Either way, when you have to plug in g of x into f of x and get out x, and plug in f of x into g of x equals x for all inputs x. Now that's the technical definition, but usually there's a better way of thinking about it. And I'd like to show you a bunch of statements that if f and g are inverses, are all the same thing. If I say a comma b is on f, then that's the same thing as saying that f of a equals b. That's always true. And we also would say that if f of a equals b, based on this, we could take the inverse function of both sides and get out this statement. Now, the definition of inverse function says this: if we plug one function into the other, then we get out whatever the original input was. That's what's going on here. We take a function and its inverse, we should get out the original input. So this is saying that that is the same thing as f inverse of b. So that means that's the same thing as saying b comma a is on f inverse. In other words, if you look at the big picture, if you have a function, that's a really bad circling job. If you have a function and a point on the function, if you switch the x and the y coordinates, the input and the output, that's on the inverse function. That's the easier way of thinking about an inverse function. That if you switch the input and the output of a function, you get the inverse. But this is the technical definition, that when you substitute one function into the other, you get out x. What we just said was that if we switch the x and the y coordinates of a function, then that will become the inverse function. So let's look at this. This is the point 2 comma 4. If we switch that, it becomes 4 comma 2. This is 1 comma 2, 2 comma 1. 0 comma 1, 1 comma 0. That's negative 1 comma 1 half, 1 half comma negative 1. Negative 2 and a comma 1/4, 1/4 comma negative 2. And if we continue this pattern, we'll see how these two graphs are related. And this is a pattern that you will always get when you have two inverse functions. That you'll see that there's this dotted line between the two. I thought I was going to get an actual line out of that. That we have a dotted line between the two. And that dotted line is diagonally through the coordinate plane. Hopefully you remember that if we're going right one and up one, that means that this line is y equals x. So it's always a reflection over y equals x. Incidentally, these are functions that you've already seen before, y equals 2 to the x. And its inverse function, which you probably know, is log base 2 of x. So whenever we have inverse functions, they are always reflections over the diagonal line y equals x. Now this definition I've been told you've seen before. A one-to-one function. A function is one-to-one if the y coordinates are different whenever the x-coordinates are different. That's what this means. When you plug it into the function, you get out different y-coordinates for different x-coordinates. If we say a function is one-to-one, then it is invertible. The reason that we say that is because if we go back here, we know that something is a function if each input has exactly one output. Well, here, this is the same thing as saying each output has exactly one input. And that's what one-to-one says. Each output has a different input. So each output having a different input is the definition of one-to-one. So if a function is one-to-one, then it has an inverse. You can say having an inverse is being invertible. And we can check that a function is one-to-one with the horizontal line test. So which of these functions are one-to-one? Well, let's use the horizontal line test. I have a horizontal line. It goes through here, and it clearly hits 2 points with the same y-coordinate and different x-coordinates. So this is not one-to-one. Here, this seems to be passing the horizontal line test. Therefore, it is one-to-one. And we can say that this has an inverse. What about over here? This appears to be passing the horizontal line test. So yep, that is a one-to-one function. And it has an inverse. Over here, it's passing the horizontal line test there. It's passing the horizontal line test here. But it's not passing the horizontal line test everywhere, which means that it's not one-to-one. As long as a single output appears twice, so for example, the output 2 appears 3 times. Once an output appears multiple times, then it can't be invertible, because then that would be saying the inverse has the input of 2 going to multiple outputs, and that's not okay. And actually, if you look back at what these functions are, absolute value function, we haven't found an inverse of an absolute value function. If we take the inverse of a square root function, we know that's x squared. We have found inverses of rational functions a few times. And, oops, deleted the wrong thing. When we have a cubic function, we haven't generally been finding inverses of cubic functions. It's possible sometimes, but not always. All right, that's inverse functions.